Okay, sorry. My name is José Rodrigo Vilca Vargas. I'm from the Católica University, San Pablo in Arequipa, Peru. And we are presenting today our paper that it's called Monocular Camera Calibration using Projective Invariants. Okay. We have here a little overview. We're going to start with the introduction with some basic concepts of projective invariants. We're going to expose our proposed method, the results that we got, the accuracy comparison, finally the conclusions and the further work. Okay, to start with the introduction, we know that camera calibration is an essential step in computer vision and image processing and optical measuring because it helps to improve the accuracy of every measurement in camera. Camera calibration faces some error sources as nonlinear distortion, imperfection of the calibration object, lens distortion, large uncertainty locating the control points. Usually, to face these problems, most of the modern algorithms include an iterative frontal-parallel projection, a pattern refinement step. I'm gonna apologize in advance for my English; it's not really the best. Okay, so we are proposing an optimized camera calibration method based on the use of projective invariant properties to detect invariant projective patterns that we're going to explain later, that grant stardiness and a better accuracy in the data acquisition stage and take advantage of them in the next steps, alongside the use of chance algorithm that is implemented in OpenCV. Okay, let's talk a little about projective invariants. The transformation of 3D coordinates and 2D coordinates in the image is known as camera projection. To achieve this camera projection, we need to perform some transformation that Euclidean geometry is not powerful enough to perform. But this transformation can be handled by projective geometry. In projective geometry, parallelism and orthogonality are not necessarily present and the distance between points can be affected by transformations. We're going to see some examples later. Nevertheless, there are certain properties that are not affected in projective transformations that are called projective invariants. Between these projective invariants, we have the properties of collinearity and coplanarity. Okay, for collinearity, we have a defined set of points that is considered collinear if every point rests on a same line. We have this equation here that says that any pair of points in R2 will always be collinear, but for a set of 3 points, we must define this matrix, where if the determinant is not equal to 0, these 3 points are not collinear. When we have a bigger set of points, each point from V3 to Vn can be calculated when the distance from each point to the line defined V1 and V2 is equal to 0. As we said previously, when every point rests on the same line. Here's an example. We can see the yellow, the green, the red, and the blue dot that have many intersections between them, okay? We have here we have 5 points that are collinear. After performing a transformation, projective transformation, we can see that the same 5 points are resting on the same line and are still collinear. We can see the same for these lines, vertically and horizontally. Talking about coplanarity, it's pretty similar, but instead of talking about lines, we're going to talk about planes. A defined set of points is considered coplanar if there is a plane that contains all set of points. Any set of 3 points in R3 will always be coplanar. But when we have at least 4 points, we have this equation where if the determinant is not equal to 0, then these 4 points are not coplanar. Similarly to the previous property, in each set of n points that belong to Rm, coplanarity of points W4 to Wn can be calculated when the distance from these points to the plane defined by W1, W2, and W3 is equal to 0. In the same way, we can see here that we have a plane containing a lot of points. Each intersection is a point. And even after performing a projective transformation, we have the points resting on the same plane. About the criteria of incidence, Incidence criteria means that 3 or more lines are concurrent. So we have 3 lines described with these equations, where if we replace the variance in this matrix, the determinant must be equal to 0. A simple way to see it is that lines are concurrent if every possible combination of lines has exactly the same intersection point. Here's an example. We can see here that at least 3 lines are intersecting in the same point, that it's the middle of this plane. And after performing a projective transformation, these 3 lines still are intersecting in the same point. They are not having different points of intersection. The third property that we are seeing today is cross relations. Cross relations are product of 2 relations. Hence, each cross relation needs at least 4 different values. In our method, we're going to use the collinear points cross relation and the concurrent lines cross relation. For the collinear points cross relation, we have here the product of relations, where AC, ZD, BD, and ID are the clear distances between each point. And with the concurrent lines, we have the angle that's formed by the lines AC, BC, BD, AD. We can see here the examples where these are the segments of the lines AD, BD, AC, BC, and here are the angles that are formed by each line, by the line A, B, C, and D. Okay, let's talk a little about our proposed method. First, we need to talk about the calibration pattern that we proposed. We proposed a calibration pattern of concentric ellipses with 5 by 4 rows by columns for some reasons. First of all, we decided to use concentric ellipses because the centroids are more exact. We decided to use this distribution of concentric ellipses because it helps us to perform some of the projective invariant properties as collinearity and cross-angle relationship. Sorry. Okay, so our method has 5 principal steps. The first one is control points detection. The second one is the frame selection. The third one is the first camera calibration. The fourth one is the control points refinement. And the fifth one is camera calibration and results convergence. Okay, we are gonna see my face a lot here. Okay, in the first step, we have four sub-steps that are masking, adaptive threshold, find contours, and find ellipses. First of all, we perform the masking, where we are gonna try to have the pattern in the minimum possible area, so we will not process the whole image, just the part where is the pattern. After we masked our pattern, we are going to perform an adaptive threshold to separate background for the foreground, so we can see better the ellipses of the pattern. Then we are going to perform the function find contours, so we can define each ellipse in our pattern. We can see here that we perform a hierarchy of ellipses, sorry, where we have in red the sun contour and in green the father contour that we are gonna need to identify the valid control points. Then we have our process of find ellipses. First of all, we're gonna calculate ellipse center. To calculate our ellipse center, we are gonna find the center of each ellipse, the ellipse sun and the ellipse father, and we're gonna calculate the average of those ellipses. Once we have our calibration points, we're gonna perform our process of control points representation and tracking, where we are gonna enumerate our control points from 0 to 19 to help this algorithm to find each point more easily and faster. The second step is the frame selection, that consists of two substeps. The first one is the initial selection. We are gonna define a grill uh, where we are gonna try to find the pattern, the pattern alongside all the frame. We are gonna try to find at least one one Bailey frame on each of these quadrants. We can see here a representation. Here it's the image. We're gonna try to find the center of each pattern in each frame that belongs to each circle defined in the grill. The second substep is the selection by projective invariants, where we are gonna identify the collinearity and the cross-angle relationship of our control points. Here we can see the collinearity of the 20 points, where each line tries to find the distance between the baseline and our control point. We have defined here a threshold of error just because there's always a little bit of distortion. In the same way, we're gonna find a cross-angle relationship that is evaluated with this equation, where the sin of 90 degrees divided by the sin of 45 degrees multiplied by the sin of 90 degrees divided by the sin of 135 degrees. It's similar to this equation that we have seen before. We showed here what's the relation of the lines that we have to see to perform this step. The third step is the first camera calibration. The first camera calibration, we're gonna perform it with the OpenCV method. After collecting an established quantity of frames that we define in the grill, related to their position on the image quadrants and their control points quality, we proceed to perform an initial camera calibration. Here we can see a little bit of the process that we have the initial frame, the invariant projective properties, and the line representation. Okay, after we perform the first camera calibration, we're gonna perform a frontal parallel projection where we are gonna try to reproject the pattern, the camera calibration pattern in a frontal parallel frame. As we can see here, it's exactly the same frame, but just reprojected. After we reprojected the image frontal parallel, we're gonna find here the control points, the 20 control points. And these control points, we are gonna reproject them in the original image. Once we reprojected in the original image, we're gonna perform a function to update our control points based on the first encountered control points and the newly control points reprojected in the image. Once we have our new control points updated, we want to perform the same process of projective invariant selections based on collinearity and cross-angle relationship. Sorry, it went a little bit of Spanish here. The last step is the iterative calibration and the results convergence. Once our refinement process is complete, we perform another camera calibration. We are gonna compare the RMS from the last calibration and the previous one to see if the difference is greater than our convergence threshold. Then the obtained camera matrix and RMS becomes the new data to perform the control points refinement process in the next iteration. We have here an example starting from iteration 36, where we can see that the RMS is 0.000653, and it's getting lower or higher until it gets lower than 0.00005. And here is the best result that we found. Okay, to collect the results, we performed 3 experiment sets. The first one is the algorithm selection, where we performed 4 versions of our algorithm to pick the version with the best results. These versions are the iterative, the iterative collinearity with angle cross relationship, and the iterative with both projective invariant properties. The second experiment is the relative distance of the calibration pattern, where we perform our method positioning the calibration pattern at different distances from the camera. That's close, medium, far, and varied, that are like half a meter, and a meter and a half. Finally, the performance of the best selected algorithm, where we test the performance of the best algorithm for the first experiment combined with the distance of the second experiment to get the general performance of the best selected algorithm. Okay, for the first experiment, the algorithm selection, we can see here the base results, that we have the OpenCV algorithm as base to compare our results, the OpenCV iterative, and our method iterative with projective invariants, where we can see that the percentage of improvement is pretty high, where we can see the OpenCV iterative that was proposed by data et al. It has just a 15.45% of improvement. Our method gets 45.18% of improvement, and in each case, it's really greater than other improvements. We tested these experiments with 4 different webcams, with HP vision, that is a camera integrated in my HP laptop, a Genius Facecam 1000X, a PS3i camera, and a Logitech Brio 4K Pro Cam. In the relative distance of the calibration pattern, we can see here some images where the pattern is positioned close, medium, and far. As I said, it's half a meter, and a meter and a half. We can see here the difference between the number of iterations and the percentage of improvement, where we can see that the number of iteration is less when we position the calibration pattern at a medium distance, but the percentage of improvement is greater when we position the calibration pattern at a varied distances. Here we can see it graphically. We came to a conclusion that even though the number of iteration is less when it positioned at a medium distance, it gets an average number of iteration when it's positioned at varied distance. So we came to a conclusion that the varied distances is the best way to put our camera calibration pattern. About the performance of the best selected algorithm, we used the same 4 cameras and evaluated 4 distances of HP vision. We can see here the number of iteration, the RMS of OpenCV, and the RMS of our method. When we can see that the percentage of improvement of our method is pretty high, coming from 29.81 to almost 45%. Finally, we perform an accuracy comparison. We use April tag to detect the distance between the camera and the pattern. We tie the pattern to the camera with a nylon thread, and we tied it with a nylon thread to get the less obstruction possible at a distance of 30.7 centimeters. Also, the position of the pattern was placed throughout all the frame to detect possible distortions in the borders, so we can have so many varied errors as possible. We performed this experiment with 6 different variations of camera calibration. First, OpenCV, distorted and undistorted. Then our method, distorted and undistorted. And finally, Bouquet's method with distorted and undistorted. The difference with distorted and undistorted method are there. When it's distorted, we just use the camera calibration matrix. And when it's undistorted, we use the distortion coefficient to test this experiment. Okay, we are gonna use OpenCV distorted as the base to find our results. We can see here that when use OpenCV and distorted with the distortion coefficients, it gives an improvement of 8.69%, but our method still performs so much better with 16.32 and 18.75% of improvement. Bouquet's method got really really bad with minus 75.35% and minus 167 and 0.7, sorry, 167.64% of improvement. Okay, so we can see that our method using the distortion coefficients gets better than some methods that are used in the literature, like the OpenCV method that was proposed by Shang or the Bouquet method. Finally, with the conclusions, we can see that our tests demonstrate that the proposed method brings a great improvement in camera calibration quality compared with one of the most used methods like OpenCV. The sector segmentation brings a robust calibration thanks to the well-distributed control points. The proposed method brings its best performance when the calibration pattern is allocated in varied distances during data collection. The use of a convergence threshold grants us the certainty to achieve an optimum camera calibration, and the use of projective invariant properties allows us to discard false positive potential frames in frame selection caused by distortion in the frontal parallel projection and reparation processes. For the future work, we propose three proposals. We propose to study the relation between average collinearity and average cross-angle relationship errors and camera distortion, so that the static distortion parameters in camera calibration could be selected efficiently and automatically. We propose to model a new cost function to validate the reparation error of the pattern centroids. Finally, we propose the implementation of techniques that automatically improve the acquisition of quality control points to increase the robustness of the proposed method based on distance of the calibration pattern for the camera or the angle of the calibration pattern, like position recommendation. We can see some of the results before and after the calibration. This is with HP True Vision camera from a close distance. From a medium distance, we can see here a little black space where the calibration was made. We can see some lines that are supposed to be straight, but before the calibration are not really straight, and after the calibration, they look way much better. And finally, the far. And when we position the pattern calibration camera, the camera calibration pattern at a varied distances, that in the same way, these lines are supposed to be straight. With Genius Face camera, with Logitech camera, that's actually the camera that we are seeing now. And the most distinctive is with the PS3i camera, where we can see that these lines are a desk that was supposed to be really straight lines. But after the calibration, they are way much better than before.